Okay, we're ready to start. Please stop me if something is not being clear and so on. This time we have like much less content and much more time, so we can go slowly. We can go back to anything that we already talked about. We can go to the blackboard. So cool. Oh no. What? Maybe it's just because it's inactive. Yeah. Cool, cool. All right. Let's get started. So we have a roadmap. Even before, so this is what we will do. Let's try to recall what we kind of did in kind of the previous lectures. So the main thing we did was we defined what a group was. That's a set with a given operation and inverses. And we define what representations are. There are just maps between two groups. The group, the abstract group that we want to map and make act on vector spaces, and the unitary operators on that vector space. It's a way to embody a group with an action on a vector space. And we like vector spaces in quantum computing, right? They are the state spaces of our quantum registers. So it's relevant piece of math for us. Once we have groups, representations, we also talked about these matrix algebras. Like the kind of demystification is like you just need to think that they are just sets of matrices that share a common block structure. So basically, it's like literally if you just take all the matrices of like size d by d, this is a matrix algebra. You multiply any two matrices and it will be a d by d matrix, right? You cannot go out of that. Cool. But what we did is what now we kind of take a group and send it to matrices and now take linear combination of these things. And because we knew that these represented group elements in some bases that we call the Fourier basis had a kind of block diagonal form, when we take linear combinations of these things, the unitaries in the blocks now kind of will span the full dense blocks. They will be kind of now the end or the linear operators in this kind of vector spaces, irreducible vector spaces, right? So essentially, we construct now these sets of block diagonal dense blocks or matrices, which are themselves algebras and are subalgebras of the dense d by d things. And we landed at this result of the double commutant theorem that says whenever I look at the algebra, matrix algebra of my group, there's always another matrix algebra called the commutant, that is stuff that commutes with this guy. And there's a duality in the sense that the things that commute with the commutant are the matrix things themselves. We will get to this, but I just wanted to have this big picture. So as I was saying, we will review this double commutant theorem, stating that the matrix algebra of any group representation and its commutant algebra dual, and a way to say this is mutually centralizing, and this implies that, yes, questions, great. Yes, but they are Neumann algebras. Yes, we're not like they are matrix algebras. Okay. Okay, this implies that the irreps, so the block structure, can be labeled in a common way. Because again, like the only thing, if you have something that has, remember, the whole idea was that you have a block structure, but there's two kind of loops. There's the outer loop where you go for different irreps, but when you have like the block of a given irrep, then these blocks that are dense they are repeated, the same block many times. So maybe let's draw this because this is very important. So I'm saying, for example, Okay, so what I'm trying to say is arbitrary representation. There is a change of basis in which it is block diagonal. These are the unitary blocks. So these are little blocks. This was like large D by D blocks. So these are D by D unitaries. You can always find a change of basis that the whole set of order G D by D unitaries now looks in the same basis as these little matrices. These are D gamma by D gamma unitaries. Repeated many times, repeated a number of times, called the multiplicity of gamma, M gamma. This is completely general. It will happen for every compact group, which includes Lie groups and finite groups over the complex numbers. So representations of compact groups over complex numbers. The next thing I said is, okay, and now if I even take linear combinations of these things and I define literally, I could first take linear combinations on the group and then use the same, extend the homomorphism by linearity. So now I think R will not only map group elements, will map this whole abstract group algebra into, now you cannot map it to unitaries anymore, but you will map it to something we can call linear operators on H, which is this algebra we were calling L, which is the D by D matrices. Great, so now we're mapping the whole group algebra there, and the claim is that, of course, in general, when the image of this map is not the full L, the image of R is this thing we're calling A. When we send all the formal linear combinations of group elements with arbitrary complex coefficients, we send them through there. We don't get all linear operators. We get a subalgebra of linear operators. Which subalgebra? Well, we already know this decomposition. So the subalgebra that we will get will be the kind of block diagonal matrices with the blocks, dense blocks like this here, same block repeated. So if we call this, I don't know, A, or we could do A gamma, A gamma, A gamma, and A gamma is an arbitrary C D gamma by D gamma matrix. Okay. I argue that this is an algebra also, it's a subalgebra of all D by D matrices, and there will be a kind of a related structure that's called the commutant that will look in the same basis. It will look very similar, but in these blocks that I'm putting here is the opposite structure. Instead of having something like A times identity, they will have identity times B, something like this. Are we following? I mean, if someone has a question, it's the moment, so we can get started. But this is what we need from last time. Yeah, please. No. Mm-hmm. How this preserves? Okay, yeah. I mean, how what preserves the block structure? That is the block structure. It's not that it preserves it. But anyways, let's kind of step down a second. Let's say we have a tensor product vector space. Okay, dimensions dv and dw. We have linear operators, which are matrices of dimension dv, and then we have tensor. These are the linear operators on this vector space, tensor product vector space. All right. Suppose I tell you what is the set of operators that commutes with something dense here. It has to be an identity here. It basically, okay, let's say A, I define it like this, tensor identity here. I'm asking, what's the thing that commutes with this? Well, it's like something like this, right? something dense here. The rest of it is just like a block structure that is kind of an outer loop of that. It's just saying there's a direct sum of multiple of this. But the important thing is happening there. Is this, I mean, we can iterate, like, is this answering or not really? Like, uh-huh. You mean, there, you would think that, yeah. I mean, you're saying that, okay, let's try something. There I wrote, so if I do A tensor identity 2 and A is some like 2x2 matrix. Yeah, exactly. So I expect this to look like this. And here is like a 0, 0, 0, 0, 0, 0, 0, 0, right? Maybe. It could be. It could be. I mean, yes, okay. This is so, I mean, it's, if it's that's not too hard. Like, just like use the opposite. When I'm totally great. If that's the doubt, that there's no problem. Yeah, it's like whatever you know better. In this case, I never remember which of them is. Sorry. Good. Great. I mean, it doesn't matter in the sense that it's arbitrary what I'm putting first and second, right? Like, I just like, yeah, yeah. It's a good time. We are established kind of, we have established conversations, so it's a good time to ask something. No, okay, we start. Yeah, okay. As I said, we will review the double commutant theorem. It implies that this block structure happens in a correlated way. An instance of double commutant theorem that is relevant to quantum info is that of Schur duality, that states that is the case where the group is permutations and the representation is qubit permutations, and you get the matrix algebra of qubit permutation, and the commutant is the matrix algebra of local unitaries. And then we have this decomposition into partitions of n. Maybe let's do this like lambda b dash d n means we have something with like at most d boxes, d rows, and if we count kind of the number of boxes we put, this is n, the number of boxes. And those things label at the same time irreps of symmetric group and unitary group, and moreover, the irreps that appear in the tensor are the same at the same time. That's kind of very non-trivial. In principle, the irreps, so in this case, you're looking at this CD tensor n as a module for the action of both things, permutations and unitaries. In principle, if you have this kind of a tensor group acting on a vector space, so you have like, let's say, group G times F on some vector space B. The irreps of this thing are any order pair of irreps of G and F. So let's call it like lambda G, lambda F. The fact that they happen, these are independent. In principle, I could have the different things, but here they're happening at the same time, the same thing, which is pretty kind of remarkable. Okay, the basis achieving this decomposition is called the Schur basis, and the kind of the transform that takes the computational basis to the Schur basis is called the Schur transform. This is nice to know. Like one, like maybe it was not clear, but like in this basis, both groups act as diagonally as possible. They mix vectors as minimally as possible. Okay. In fact, in certain of the kind of the in certain of these things, like whenever like the representations are one dimensional, they do this is eigenbasis for these things, but not in general because they're non-abelian groups. If the groups were an abelian, then you would get literally the sure basis, and there is the eigenbasis in a sense of the whole group. Well, the Fourier basis is the eigenbasis of the whole group. Okay. Period. We know what the sure transform is. Well, some people called Bacon, Childs, and Harrow came up with the idea of compiling this unitary into a quantum circuit and using it for quantum information tasks. Any such circuit is called a quantum sure transform. We will review original construction. Then there's a high dimensional proposal or Kroby, and then we have some results. And then we will explore applications of quantum sure transform to fermionic state preparation in first quantization and memory savings when storing many copies of a state. Okay, let's get started. That's the outline. Okay, double commutant theorem, general duality for arbitrary group reps. This is what I already discussed here, but again, the notation G, R, some vector space CD, some matrix algebra A, and some other matrix algebra C that are mutually contain the things that commute with each other. Okay. The commutant of the commutant is A itself. For example, when you have qubit permutations, the commutant are local unitaries, and so on. As I was saying here, the irreps. So we also saw representation theory of unitary and symmetric group and learn how to produce for a given partition, how to produce the irreps, what are the matrix elements, what are the dimension of the irreps and everything. But if you don't remember it, at least remember that they label the irreps, and I will call V lambda irreps of the symmetric group. This is just a vector space, but it's not just a vector space. It's a vector space of certain dimension and with certain basis that the group has an irreducible action on. And then irreps of the unitary group we call W lambda. Okay. As I said, there are special bases, canonical bases that are related to paths in the restriction of the irrep down a chain of multiplicity free restrictions for these subgroup chains. Sn minus 1 or ud minus 1 and so on. Okay, maybe we ask questions here. Yes. Sorry. Yeah, maybe it was a little fast. Yes. Yeah. That's a good idea. Maybe just here. I don't need to go too far away. This is good idea. I think we have the dimensions were somewhere in the second lecture. Let's do this very fast. This is a good example, I think. So the whole idea is that there is, what is it? C2 tensor 4. This thing has a computational basis, right? X1 to X4, each X is like a qubit. This is a computational basis, and the claim is that there's another basis that you can label lambda Tm, where lambda is in these diagrams up there. So maybe we can even draw it like this. Be real nicer. say. Lambda is one of these choices. And then for each choice of lambda, there are different choices for TNMM. What are there? Okay, let's take one. Let's take this one to begin with. As a representation of the symmetric group, this is one-dimensional, and you can see this because there's only one way of putting the numbers 1 to n and respecting the conditions that we talked about, like the fact that they need to be increasing both to the right and down. Okay, I need to put numbers inside of this thing. So I put 1, 2, 3, 4. That's the only thing I can do. It means there's only one path. We can also see this as a path thing because we can draw the diagram. I can do this like. Now we go like here, here. You can see if you need to get from here to here, there's only one path. This means that the representation of the symmetric group is one-dimensional. So if I now write this, I write the following state. There's a state in the Schur basis that is kind of this diagram. Good. This is a ket, okay? This is a ket, and then I need to put M here. M has several choices. What are the choices? You need to take the partition, which was like partition 4, and pad with zeros all the way up to the dimension, which is 2. So you put like 4, 0, and then you need to kind of come down in all possible ways with interlacing relationships. That means that you put a number between these two things. So you can put like here, you can put 3, 2, or 1. And then, yeah, it's something like I'm getting kind of confused here. But what I can tell you very fast is also that these kind of diagrams, this Gelfand-Celsin pattern, in this case, they're simple because since it's SU2, this is the spin 4 halves, so spin 2 case. There are 5 possible spin projections of this guy. So in a sense, this guy is telling me irrep of Sn is trivial and irrep of SU2 is 4 halves. So 2. So here we should have like +2, +1, -1, -2. 4 possible states. That's the first block of the Schur basis. So you could come, and so the isotypic, like corresponding to this thing, will have, if I look at the representation of a permutation, any permutation in this 4x4 block will look trivial because this is the only path and repeated 4 times for each kind of irrep of the unitary group. So this is kind of something like identity 1 tensor. Sorry, it's like R lambda, but lambda being this kind of partition R4, which is trivial. It's a 1x1 matrix of sigma. Tensor identity 4. Now if we look at, let's use P here. Let's use Q of a unitary. This will be a little bit more interesting. In this block, it will be like one copy of this kind of spin 2 representation. We can call it Q S equal to of the unitary. So it's a 4x4 matrix corresponding to, for example, if the unitary is X, the thing that you will see here is like JX S equal to 4x4 matrix. Are we following? Is this kind of better or worse than slides? Better. Combine. So let's move on. The only thing that I wanted to say is like you can then come and do this guy, for example. you count the paths, there will be, I think, 3 paths, and there will be, yeah, let's say, let's do it very fast, so that you see where this is going. You have this height, they have 3 paths, which correspond to 1, 2, 3, 4, 1, 2, 4, 3, and 1, 2, 3, 4. And then there are, this was spin 2, right? I said it. There are 5 things. I'm missing a state here, sorry. And there will be a 1, there will be a 5, 5. I'm sorry, but it's just spin 2, this is a 5 by 5 thing. Cool. Sorry. Yeah, the rest is okay. Now, spin 1 is 3. So you have +1, 0, and -1. These are all possible states of the second isotypic that we are looking at. The second isotypic is 9 by 9. And if you look at kind of, for example, reps of something, there will be 3 by 3 blocks like this. Yes. Yeah. Oh, no. Yeah, this is completely decoupled, I think. Or not completely decoupled, but I will explain how to do the basis transformation today. Yeah. And in fact, like you can already see that whatever you does this transformation, and now think of a different U that kind of mixes the bases here, it's doing the same decomposition in a sense, okay? So there are kind of, there's a freedom. There's a freedom for the Fourier base. But it's not too hard. Like all I'm saying is, I will call a Fourier transform everything that achieves this decomposition. Yeah, and exactly. Yeah. But in fact, I will ask for this kind of specific basis that I already defined. But in principle, you can use different bases than those, and I guess it's still a Fourier transform in that sense. How to find the U, or how to find or build a circuit for, like in your computer. Yeah. I know, that's great. There's a simple way to do that, actually. If you just wanted to kind of compute it, like the matrix entries of the unitary, you can do that. Yeah, you can do that. In your computer, yes. It's a different question to building the circuit, okay? But if you want the matrix elements, we can do this. I think it's easier. I remember out the back of my head for another duality, which is the duality between left and right regular representations. Yeah. No, but it's a good, I think like, I mean, yeah, so essentially the U will look like lambda Tm and sum over X. I mean, this is stupid what I'm going to say, right? Like, I'm not doing much. And I'm going to put here some coefficients. And you're asking, who are these coefficients? Yeah. No. It's a good question. The Clebsch-Gordon coefficients would be, we can like do this. It's another kind of, this is UQST, U Clebsch-Gordon. It's like something like, if you have, let's say, unitary group E reps, so we will use like M1 and M2, which have some shape like, I don't know, it could be lambda 1 and lambda 2, whatever. So we have 2 E reps in a particular Gelfand Selzin pattern each, with define a specific basis state, and now I'm tensoring them. So it's a tensor basis. Tensor. By definition, there is another basis we can call the coupled basis, that in the tensor basis, the group action is not block diagonal. But we can have another kind of basis here, which will be kind of lambda m. And then I need another kind of label for multiplicity, like I. And that's basically it. Now, this basically I'm saying these things coupled to this. So if these are spins, these are kind of S1 and S2 in a given M1 projection and M2 projection of spin, something between like minus S1 and so on, whatever. And this will be the total spin that they're coupled to and the total projection. And there's no, because it's spins, there's never multiplicity when in the Clebsch-Gordon. But in general, for larger D, SUD kind of tensors, you will get multiplicities. Irreps appear more than once. But yeah, besides that, this is the Clebsch-Gordon transform. And here there's a Clebsch-Gordon coefficient. Okay, we were doing this example. We were doing okay, right? We did the first block and the second block, and I guess from here we can kind of just come back to what we were doing, except we're okay? All right. Cool. Schur transform. Oh, we need to make it. Why is this? Oh, what's going on? Yeah. So we said this many times. It's a unitary that achieves the block diagonal form of the permutation and unitary action. It takes the computational basis to, I mean, this is literally the equation I wrote there, right? For the matrix elements, without saying explicitly who the matrix elements are or how to compute them. But I'm saying there is this kind of, you can even either think lambda Tm is a state, like, and you can define it like as I was doing here, like linear combination of the computational basis, or you can think lambda Tm is like, it's a tensor of registers. Like, it depends if you're implementing the Schur transform unitarily or in an isometry. I think it's easier to think of isometries here, just like think that you're going from one register to three registers, and the kind of valid combinations of states that appear in this three register system are those with CTM different than zero that involve T and M of shape lambda. Okay. Okay. Right. So we know what Schur transform is. We want to speak about the quantum Schur transform as the kind of circuit that compiles the Schur transform. It was developed by Bacon, Childs, and Harrow in 2005. The construction has a time complexity that is n times d to the 4. So it's polynomial in n and d, and d square space. Here you need to notice that yes, there was a conjecture originally in their work that this should be possible to have a construction with like polynomial in log d, not in d, and that's kind of a huge kind of difference. In particular, in certain tasks, not in all tasks, but in certain tasks, you may really kind of require large d, and d kind of, for example, d much larger than n. You have few copies of a very, very high dimensional, potentially also tensor. You have a tensor product system, and then you have few copies of it, and you want to do some quantum information task on it. In that case, the polynomial in D4 is kind of terrible. So people try to construct these high dimensional Schur transforms, and the proposal in 2018 by Harry Crowley was based on a very different construction as corresponding to the VCH. It's completely different. I will explain the VCH today. It's based on Clebsch-Gordon transforms. So it's kind of coming from the unitary group side, and Crowley's approach comes from the symmetric group side. Okay. Yes, I mean, yes, it's a mistake in the sense that it's not achieving the right basis, the right Gelfand-Selzing basis in the end. Yes. So yeah, I mean, that's why it was kind of important to try to understand the mistake and try to fix it. And we will see. We'll discuss a little bit the results there, because many also kind of lots of protocols kind of build upon this construction, build on the assumption that you can do high dimensional transforms. Okay, and the result is you can do it. So that's what we're gonna get there. Okay. So we said it many times. We want to do this isometry. I even draw this here. There's a Young graph, and the path is given by these standard tableaus where you put numbers in a certain way, but you can also use Yamanouchi words, which are basically saying on which row I'm going to put the next box. And it's if you use paths represented by this kind of thing or this kind of thing, you get different encodings of the basis. It's the same basis, but you have different encoding, and the circuits are different, and the kind of the space you're using are different. So I will particularly use the last one. I find it more natural. But okay, it's a detail. I guess the idea is to convey the high-level picture, and it's that the Schur transform is a cascade of Clebsch-Gordan transform. So what's a Clebsch-Gordan transform? I kind of explained there, the Clebsch-Gordan transform is the diagonalizing the tensor of two irreps of the unitary group. In particular, we don't know efficient circuits for the tensor of two irreps, for the diagonalization of the tensor of two irreps, but we do know the case where one of the two irreps is the standard irrep. So that's what we're gonna use. We'll define kind of this. So this is what we wanna do: one irrep and a standard irrep. This has to break into irreps again, and the claim is that the irreps that appear are these ones with multiplicity 1. And that's called Pieri's rule. And here, this is the addable cells. So if you have some diagram, you cannot put the new box anywhere. So there's a set of possible places where you can put a new box. And those are the new diagrams that you iterate over. And as I was saying, there's an efficient circuit that will achieve this transform, that will map a given basis vector for the non-trivial irrep, well, like non-standard irrep, a basis vector of the standard irrep and an ancilla to a basis vector of the lambda plus A irrep and a box A that encodes path information, so like symmetric group essential information. We will see how to use. So this is the picture, again, the kind of lambda irrep, standard irrep, and here we get lambda plus A. And we use this little block in the following sense. We put these blocks like in a cascade. They call like what you want. You want coming with like a n-qubit basis, computational basis, and you want to output an M that is kind of a unitary group basis. You want a path for a symmetric group basis, and of course you want a lambda, but the lambda is encoded by this yn here. So it's just there. I mean, it's not in the drawing, but it's there. So how do you do this? Again, you bring the qubit registers one by one. And remember, each time you have a qubit register and something that is non-trivial, this you can do it with the Clebsch-Gordan transform. So at each point, for example, this point, incoming is a given kind of lambda k mk irrep basis, and then you bring this standard irrep and you kind of couple them and so on. And each time you produce a label for the path. So you collect the labels for the path. That's the basis element of the symmetric group irrep, and this guy is the unitary group irrep. Okay, rough idea maybe to have today. I think this is clear roughly. This is the paper I was kind of mentioning. we fixed the mistake. I will not talk about this because it involves explaining Kravis QST, and it's like there's no way we can do this today, or in like with the we need to introduce lots of stuff, more representation theory of the symmetric group, permutation modules, and so on. We will not do this, but I wanted to state the result, that is that we get time complexity that's n to the 3/2. Pretty good. And the thing that I'm going to talk about is that you can also fix the original construction to be high dimensional. And you can achieve this time complexity. That is essentially, if you have D that is very large, forget about this guy, and you get time complexity n to the 5, n to the 5, and 5th, something like this. So still, this is better in a high dimensional regime. It's similar. It's near, and conceptually, this is much easier, way easier. Okay. So that's why we were going to explain the second one. So let's explain the construction. Yeah, this is, I already said this. The trick is that BCH has this complexity, n d to the 4, but we can make d is the dimension of the local registers. You have n different local registers and different qubits. There's a trick that you can like compress each qubit into a qnit with n equal d, with d equal n, and then apply BCH normally there. So you will basically have n times n to the 4, which is n to the 5. That's all we do. We compress, we apply BCH, and then we kind of decode. Yeah. Well, I explain now. This is what I'm trying to give the idea, but let's see what I mean by compress. So by compress, I mean we build a reversible map. So kind of a classical reversible circuit that will take a dit string into a pair EP, where E is a string of length n. This is a string of length n in a D-ARY alphabet. And think of D being very large, let's say 100, and n being small, let's say 10. So you have a vector where the entries can be like 99, 98, 70, whatever, but it's like short. And now you go to something with not with constrained things in the entries, and also short, and a large and a decoding string, which is in the same space as this one. Let's see why. How? So as I'm saying, let's say like you have some small n and a large d, and you have this vector, this string, 100 to the 6. And then I will use two different strings to encode this guy. How? I will use E to encode the different things that appear here, but like, for example, the smallest 2 will go to 1. The next smallest 5 will go to 2, and so on. I just compress it in the sense. Yeah. So again, like the third smallest is 11, so it goes to 3. The fourth smallest is 99, that goes to 4. Well, there's a problem there. I think I did it in the wrong way. Well, like it should be like that. And then we have P that essentially tells me how to reconstruct X with the following equation. Evaluate, so to get the ith end, so you encode, you keep E and P, and you throw it X. And if you want like the ith entry of X, just do P on EI. So let's see if it works. We want the fourth entry of X, which is 1, 2, 3, 4, 99. What this equation is saying is you can do it from P and E. How? Evaluate on PEI. PE4, So P E4, but E4 is 1, 2, 3, 4. It's a 3. So this PE should be P3, sorry. And P3 is 1, 2, 3, 99. So we recover 99 from these two things. That's encoding. And it can be implemented like with a reversible circuit, and it can be therefore put into a coherent quantum circuit. So this is the quantum circuit for the high dimensional VCH. This first thing, so we have the input X, an ended string, we apply P, we get the is and a P. The P we just keep to the end. And the is we send through VCH, but this is a compressed VCH. It's a VCH on N and D equal N. When we kind of find the output of VCH, the path and the label, they don't depend on like the symbols here. So they are kind of okay. The only thing that depended on the choice of like on this compression and or like kind of a relabeling of like the local elements, obviously, is the UD register. And then we just use this kind of, call it the coding or fix of this guy into the correct M using the P information. That's it. Okay. Any questions? We are doing good. I think we have like some applications and we are ready to close. So there are many applications. I just like took a couple that are kind of easy to explain. For example, consider fermions in first quantization. You have a single particle space that is CD. I'm saying there are d orbitals, d modes. If I take the tensor of k of these things, this is kind of the space of k distinguishable particles. So basically, like d to the k possibilities. But fermions are antisymmetric, so I need to kind of look at the antisymmetric, completely antisymmetric subspace inside of H tensor K. This thing has dimension d to the k, and this thing has dimension d choose k. That's kind of very different. Like, let's see, d to the k versus d choose k. Am I saying right? Yeah. 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 Okay. Let's move. So an arbitrary physical fermionic state has this form. For every choice of a subset, yeah, exactly. For every choice of an order k subset of the d modes, I need to choose where I'm putting the particles. I need to choose where I'm putting the particles, which orbitals will be occupied. So I need to choose k things out of d. For every choice, there's a possible kind of basis state, and there's a possible kind of coefficient. Those are the physical states. The problem is that these kind of basis states are kind of very hard to prepare because they are these kind of completely antisymmetric linear combinations of computational bases. I'm calling for each subset I can define xi to be the order bit string corresponding to those occupation modes. But the complete antisymmetrization of this involves like k factorial terms with signs. So it's not really kind of obvious how to prepare a state like this, let alone kind of the linear combination in first quantization. Yeah, so what I propose here is to use the quantum Schur transform in the following way. If you fix this partition, each valid possible Gelfand-Setzlin pattern corresponds to a choice of k out of the d modes. So if any I is related to an mi essentially. Therefore, if I prepare the this kind of label, imagine yourself on the output of the Schur transform on the other side on the output. There are three registers. I prepare the partition corresponding to completely antisymmetric SN reps. I prepare, those are one dimensional, so this T doesn't have much choice. This is the kind of column of 1, 2, 3, 4K. And then MI, I choose the one corresponding to I, and then I apply the inverse Schur transform. I will get this kind of crazy linear combination of signed basis elements. That's the idea. Yeah. Just an explanation. You can also produce like kind of completely symmetric states by using here the diagram, the completely like the K, and that therefore you'll be producing bosonic states of fixed particles in first quantization. So, or like, yeah, it's an interpretation of what kind of quantum Schur transform is doing here. And then you prepare an arbitrary physical state by preparing the arbitrary kind of superposition on the Gelfand setting register, and then tensoring with 1 to the k T star and applying the inverse Schur. Cool. Right. Let's go to the final application and we can finish. Now we're gonna discuss a little bit again like Schur sampling. A Schur transform gives an explicit way of performing Schur sampling. Schur sampling means measuring just the label of after the Schur transform. More generally, like you can say, Fourier transforms give an explicit way of performing Fourier sampling, and the case Schur is just a case of a specific group representation. One can bypass the need for the fully fledged Schur using Harrow's generalized phase estimation algorithm. I think we kind of discussed it, but it looks like this. Measure, nothing here. Yeah, so here I need trivial irrep 0, 0. All of this is basically if I initialize a state, I initialize this other state, I apply this circuit, I apply this circuit, and then we measure here. Each time we get lambda, we implement a projective measurement. So all of this is a probabilistic project implementation of pi lambda. All of these things that I'm putting in a box is the isotypic projector. It's like implementing pi lambda to pi. So in the outcome, if I get lambda, now I will have like pi lambda pi as a state, pi lambda psi over its norm. And the probability will be like literally proportional to the norm. Yeah. And the whole idea is that this is equivalent to having done the following thing, having sent psi through a QFT over R, arbitrary rep, because this is the regular rep, that's a regular QFT, and this is kind of an arbitrary rep R. So if I had a QFT over this arbitrary rep R, essentially I would get like irreps lambda, something dimension, something multiplicity, and I could just measure there. But in principle, you don't really need a QFT over any representation. You just need a QFT over the regular representation and controlled actions. That's what Larocca at least proposes. So you don't, in the case of sure transform, you don't need a sure transform. You can use it. You can do it with the SNQFT. All right. I think with that we have the last slides. Come on. Oh no. Yeah. As I said, you can bypass sure transform and implement sure sampling by if you have SNQFT and a control representation, a implementation of a control R. So here comes the problem that you can solve with sure sampling. Given copies of rho, you want to compute the trace of rho to the k. If k equals 2, this is, for example, the purity of rho. Of course, you can do a swap test, right? And in fact, in a sense, a swap test can be interpreted as literally sure sampling. But okay, so for larger k, what are you going to do? For example, if you want to compute range entropies, you need to kind of take a trace of rho to the k. So I'm going to show how the quantum sure transform, or more generally sure sampling, I don't need the quantum sure transform, sure sampling can do it. Why? Okay, recall the identity. So maybe this is the representation of a qubit permutation that's just a k cycle. And then I have the tensor product of k operators. This equals the trace of the product of the operators. Have you seen this identity? Do you know it? Not. You know that swap times A tensor B is so the trace of swap times A tensor B is the product of the trace of A times B, right? We know that one. This is just a generalization to kind of K body things, okay? So if you implement a cyclic shift, you can take tensor products to products, essentially. All right. So we can write our target, let's call it A, the thing that we want to compute. We wanted to compute the trace of rho to the power k, but instead of doing that, we write it as the trace of cyclic shift and rho tensor k. So we initialize rho, k copies of rho, and we try to measure the expectation value of this unitary. In the sure basis, we know that the representation. So I'm not using the p here, but there should be a p. This is a permutation. This is a permutation, right? I'm saying it's a unitary because I'm already sending it through the homomorphism p, but implicitly here. Now here I'm explicit. This p of sigma will be irreps tensor multiplicities, like we well known in the sure basis, and conversely, the rho tensor k is permutation invariant. So in the kind of the register where permutations act, it will be maximally mixed. And on the other register, well, it may be something non-trivial. So what I'm saying is rho tensor k looks like maximally mixed tensor another state, and this is a probability distribution. That is the probability distribution, literally the one that you get when you sure sample. So you compute A using this decomposition. So you put this guy here, the direct sum goes into a sum, you get the P lambda, and then you get the trace of this guy over D lambda times the trace of rho lambda, tensor the trace of. So yeah, you get the trace of the tensor product. Something is the product of the traces, but the trace of rho lambda is 1 because it's at state, and then you get the trace of this thing, but the thing on top, this is a scalar, and the thing on top is a representation. The trace of representation is the character. So you get something like this. And when you look at this, anytime you have a, like, something that is the sum over the support of a probability distribution, and then something else, if you have access to samples from the probability distribution, you can estimate this thing as the expectation value of this thing as an estimator. So that's what you're gonna do. You're gonna say, oh, I will sample lambda and I will compute this thing and I will average. So you prepare k copies, you sample lambda, you use it to build a single shot estimator. That's got the character evaluated at the cyclic shift over d lambda. You repeat n times, compute empirical average, probably bound the variance and see what happens. This is the claim that if you average this random variable, you get the thing that you wanted to compute. It's unbiased. Something to note is that in principle, evaluating Sn characters, so each time you get lambda, you need to evaluate the character of a permutation on irrep lambda. In general, evaluating Sn characters is very, very, very hard. It's literally outside the polynomial hierarchy. Like deciding even like the positivity, if a Sn character squared is 0 or larger than 0, is C equals P hard. So it's very, very hard problem. But it is worst case. In this case, when like you have this specific permutation, in particular for any L cycle, oh, here it should be 1, 2 to L, and for any L less than K, you get that the character on any lambda, well, on only on the lambdas that look like hooks, something like this. A hook is something like this. It's a partition that has first row something, let's call it like K minus L, and here it has L boxes. So they add up to K. That are the number of copies that we have. Whenever you have that, the character is -1 to the L. That's the order of the cycle. So very easy to compute. And the dimension is also easy to compute. Like we gave a formula the other day. It's even easier, I think, here. I didn't put it, but I think it's like something like K choose L. Never mind. Like in Sn irrep dimensions are always in P to compute, so don't worry about that. So you can evaluate the estimator, and then you just bound the variance. Here I'm giving some arguments why the variance is less than 1. At this point, we're a little bit tired, I guess. We can look at it. Like, so R lambda for any permutation are d times d unitaries, and this implies that the character, which is a trace of the representation, has to be less than d lambda, right? The norm of a unitary cannot be more than the dimension, its dimension. Unitaries are normalized in that sense. Think about Pauli matrices. They have norm equal to the dimension, right? Okay, so you just bound this, you get the variance is less than 1, and then you use Hofstadter inequality, so you get that if you allow for certain probability of error delta, you will be within precision epsilon using these many shots, basically 1 over epsilon squared. Yeah, so I mean, you just sampled from Schur, you prepare Rottensor K, you sampled from the Schur distribution, and you were able to compute the trace of rho to the power K. Yes, we can discuss this. This is the same slide as the first slide, but with the past tense. So maybe we can just go over it very fast. Double commutant theorem, Schur biduality, Schur transform, Schur sampling, quantum Schur transform, and applications. Thank you. And if there are any questions. Yeah. Yes. Yeah. Yeah, full slide, sorry. Yeah. This thing. Oh yeah, yeah, yeah. I mean, excellent. If it weren't, it wouldn't be permutation invariant. I mean, that's the definition of something permutation invariant is what we have been discussing. In the sure basis, it has to look like the identity on the just okay. I can look at this. Ah, yeah, 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 for sure. The symmetric group is acting over these k copies. Yes. Yeah, 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 totally. So I claim in the sure basis, rho tensor k looks like something mixed tensor something else. Why? Because in the sure basis, any permutation looks like something here, r lambda g tensor something here. So if I want this thing to be invariant under permutations, it means that, look at it, let's do it explicitly. R sigma rho tensor k, R sigma, this what it is. It's like O plus lambda in the this operator, this new operator on the sure basis will be R lambda G. Let's say here this you're not the identity. You're like some rho lambda Sn. This is rho lambda UD. So rho lambda Sn R lambda G dagger. Tensor, oh my god. Identity. Well, tensor something else here, like the rho lambda UD. That doesn't matter. But no, 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 no. This one, no. I mean, I think it will be very no. In general, definitely not pure. No, no. But okay. So what you want now? You want to set an equality to rho tensor k because you want. I mean, you know, rho tensor k is permutation invariant, like it's explicitly. On the left hand side, it's obvious. Now on the right hand side, you want to make things match. So you write rho tensor k. You have like rho lambda Sn tensor rho lambda UD. Now you compare. This is okay, but this is not the same except these things commute because it has to happen for all G also. So the only chance that these two things are the same for all G is that this thing is identity. Yeah. I guess that's kind of an explanation. Great. Other questions? Yeah. Everything you can see from a representation theoretic viewpoint. But I yesterday I described Hind's group problem, not phase estimation. But still, yeah, 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 yeah. So QSVT is what you want? Probably. I haven't thought about it. There are there are many kind of connections. Like that GPE thing looks like a block encoding, to be honest. You know, like LCU kind of thing. I mean, you're controlling unitaries literally. You're preparing certain like prepare select kind of thing. So there's definitely some stuff there. Yeah, yeah, for sure. Yeah, yeah. It's a good question. Um, yeah, for sure. This I'm basically mostly thinking about like I mean, since I want to use these primitives, like you better have fault tolerance, right? Like they're not very near term per se. But um yes, I think it's a good question again. Like and maybe if you're here next week, I'm gonna present a fault tolerant algorithm that has large separations with the best thing we know for computing Kronecker coefficients, computing multiplicity coefficients. And it's basically using that thing there for Fourier sampling over certain reps of the symmetric group. So you just get like literally something similar to today. We sure sampled and we did something with the samples. Here's the same, but it allows you to compute Kronecker coefficients, and there are no known classical algorithms in this regime. Very constrained, like no one cares about it except mathematicians, but still it's a kind of a proof of principle of a quantum separation that is like it's arbitrary large polynomial separation. So it's pretty good. Um, so that's an algorithm. And in general, I'm trying to use all of this structure that rep theory knows how to handle to kind of put it into problems that are very well structured and you can solve nicely. I mean, we know we need structure for quantum computing too, right? So I think this is the right bias, the right structure. Awesome. And yeah, I mean, maybe something that one needs to kind of try to. I mean, or something that I am interested in is the fact that at least many of the algorithms that we like kind of like or like think they are the best we know quantum algorithms are based on Fourier stuff, Fourier transforms, Fourier sampling, hidden subgroup problem or abelian groups, Shor's algorithm and everything is based on Fourier stuff. And then we have all of this non-abelian Fourier stuff that we haven't find good applications for. But that's why I think quantum computers are good at Fourier whatever, and like and there are still Fourier problems that are not solved. Yeah. Okay. Okay. Thanks. No questions.